Welcome to the PX2816B protocol exercise or demo. The PX can operate as both an I3C controller and a target. In this demo, we'll connect two external sensors, a temperature sensor and an accelerometer. They will act as external targets. The instrument has a built-in power output port, allowing the pod to supply power directly to external devices. On the back panel, you'll find a 15 volts power supply output, along with a Type-C cable for connecting to your PC. Let's take a closer look at the cables. This is the power cable, Type-C on one end, DC output on the other. It can be powered directly from a standard gallium nitride charger. As long as the charger delivers 15 volts at 3 ampere or higher, that's all you need. If you already have a compatible charger on hand, any unit supporting 15 volts at 3 ampere output can be used to power the exerciser. Power banks with the same spec work just as well. The other cable that connects to the PC has a Type-C connector and a standard USB-A on the other end. A USB-A to Type-C adapter is also included in the accessories for added flexibility. These are the two cables you'll need for today's setup. Both power and USB are now connected. You can see both indicator lights are lit. On the software side, simply select the protocol you want to work with. There's no need to purchase separate instruments for each protocol. Let's open the I3C section. A topology view will appear for initial configuration. Enable controller mode to get started. Pull-up resistor values can be configured here as well. Go ahead and turn on the power for the external nodes. For pull-up resistance, let's say we enter 500 ohms. Since the instrument uses a fixed resolution grid, it will snap to the nearest valid value, which is displayed in the approximately value field below. The resolution grid has 4096 steps. The address table lets you predefine address assignment rules. For example, if a device's PID matches 00002, you can specify that it should be assigned a particular dynamic address first. This gives you precise control over which addresses get assigned in priority order. If there's no match, the system will shift, incrementing by 1, then 2, until it finds an available slot and assigns the closest available address. This workflow lets you pre-map your entire address space before running ENTDAA. The right panel handles I2C address assignment, where you define which addresses belong to I2C devices. You must first enter the existing I2C address of the device connected on the I3C bus, so the system correctly identifies it as a legacy I2C device. The panel below becomes populated after ENTDAA runs. It shows all currently active dynamic addresses on the bus, each paired with its corresponding PID, BCR, DCR. All the parameters defined here are synced to the exerciser for bus control. The decode panel uses the I3C protocol engine for frame parsing. Expand the detail view to see the full decoded breakdown. The timing configuration is organized into sections, starting with common, which covers the I3C push-pull clock speed. This can be set up to 13 MHz. Open drain speed has its own dedicated setting, with a maximum of 2.5 MHz. Below that, you'll find timing parameters such as TCAS and TCBP, as well as DCB and TCA repeat start values, all numerically configurable. The base unit for all these timing values is 5 nanosecond. There are additional parameters further down, including push-pull duty cycle, where you can fine-tune the high-low ratio of the clock signal. The default is 68% high, 32% low. A mixbox slider is provided for quick adjustment, but you can freely drag it to any value within the permitted range defined by the specification. The upper limit is 75%, and the lower bound is similarly enforced. Beyond push-pull, there's also optimized header control. Open drain speed is split into high-speed and low-speed modes, plus a dedicated open drain read 8 bytes mode, each independently adjustable. The I3C read and write sections are also independent. Legacy I2C clock speed is configurable here as well, up to 1 MHz. Those three groups, address table, decode, and timing, are the core exerciser parameters. Next, let's walk through the internal node configuration. The first field is the node label, used to identify which role this internal node is playing. For example, to emulate a legacy I2C device, simply select I2C. For I3C target, you can optionally enable a static address. Secondary controller mode is not yet available, so that option is currently grayed out. Support will be added in a future firmware update. The fourth mode is something quite unique. It's a dedicated stress test mode for your controller DUT. The exerciser can simulate a large number of nodes simultaneously and bombard the external controller with IBIs, verifying that it can handle high-volume interrupt scenarios without dropping events. You can dial up the node count as high as needed to stress the target controller. A word of caution though, this is an intentional stress test, and it's entirely possible for the external controller to lock up or crash. Keep that in mind. Back to the I3C node configuration. Since ENTDAA hasn't been executed yet, dynamic address shows is not assigned. Below are the target-specific settings. The first field is the I3C specification version, which determines the behavior of all downstream parameters. The register uses a 32-bit format. Select the format that fits your device's implementation. Moving on to the PID section. The manufacturer ID field defaults to Acute Technology's registered MIPI Alliance manufacturer ID, but it can be freely modified to match your device. When creating multiple nodes, the part ID field auto-increments to ensure a unique PID, BCR, and DCR combination for each node. Below that is the BCR section. Each BCR bit is individually labeled and explained, so you can understand exactly what each setting means. This is one of the key differentiators of our software. It allows you to understand every parameter at a glance, rather than entering a raw hex byte and manually cross-referencing the specification for decoding. We surface the meaning directly in the UI. For example, you can see at a glance whether advanced capabilities are supported, and whether IBI and IBI with payload are enabled, all shown clearly. For DCR, we provide a predefined reference list that lets you select a known device type to emulate, or enter a custom DCR value for your specific use case. Below that are the advanced capability settings, starting with Get Caps. Click to expand. You'll see 3 tabs at the top. Since we've selected version 1.1, this tab is disabled. In I3C 1.0, this command was named Get HDR Cap, and only indicated whether HDR was supported. That tab is therefore disabled when operating in 1.1 mode. The relevant tabs are Get Caps Format 1 and Format 2, where you define how many capability bytes this internal node will return when queried. For example, setting it to 4 means a Get Caps read will return exactly 4 bytes. Every field within the response is documented in the UI, such as the spec version field and the HDR support flags. If the Get Format 2 tab is grayed out and non-interactive, it means the caps defining byte hasn't been enabled yet. Enable it, and Format 2 becomes fully configurable. I'll also enable status here, since the Get Status response depends on the same defining byte to function correctly. Let's enable both now. The Get Caps value shown in Format 2 automatically mirrors Format 1, it represents the initial state, so no additional setup is required. We've also pre-populated the fields from the specification, including the test pattern entry, which is fully editable. CR caps and VTE caps are also available, as well as DBG caps. In addition to Get Caps, we also support Get Status. Get Status follows the same approach, each field is individually parsed and labeled. Format 2 is available here as well, with its own field definitions and format structure. MXDS is also supported. Each value's decoded meaning is automatically populated into the corresponding parameter fields. To enable max return, toggle it on here. Enable the defining byte support, and the format fields will activate for configuration. This next section lets you configure the target's maximum and minimum payload lengths, specifically MRL and MWL. The IBI fields are currently locked because the node is set to not capable, meaning IBI is disabled and all values default to 0. Some fields in this section are initialization values, while others can be updated at runtime via set MRL MWL commands. After the configuration is complete, click OK. The node hasn't been assigned yet, its connection is shown as a dashed line in the topology view. With the node added and the topology ready, confirm external power is on, then start the ENTDAA assignment process. Issue the ENTDAA command and click Run. The I3C run flow is step-based, with some steps being optional and others mandatory. The steps are: refreshing the device list and updating the topology, syncing the configuration to the instrument, choosing whether to send RSDDAA for a full bus reset, whether SetDASA needs to run first, and whether SetAASA should be applied. Check or uncheck ENTDAA as needed, then proceed. The indicator lights on the right show real-time step status: gray, step is disabled, not queued; blue, step is queued and waiting; green, step completed successfully; red, an error occurred during this step. If an error is reported, check the status bar in the bottom left or the status shown beneath for the error details. Once you've reviewed the sequence, click Start to execute. When all steps complete successfully, the indicator turns green. Close the Run dialog. The external nodes are now visible in the topology. Here are our two external nodes. Click to expand and see the node details, for instance, this temperature sensor. The manufacturer ID and associated values are all displayed in the node panel. Hovering over a node reveals additional decoded information in the tooltip. The internal node panel displays more parameters by design, since it is our emulated node and all internal states can be directly exposed. Once everything is assigned, close the panel. Since we already sent RSDDAA and ENTDAA, those transactions appear in the Protocol Analyzer report. Double-click to view the waveform. Right-drag on the waveform to check frequency. 2 MHz. The address is shown here, and this portion runs at approximately 7 to 8 MHz. This is the ENTDAA transaction, including PID, BCR, and DCR. Click on any row to view details on the right, with full field breakdown. For example, this is the decoded data from the temperature sensor. The waveform is real-time captured in live mode. Now, open the Wizard panel. The Wizard provides manual control over transactions, including private read-write, broadcast CCC, direct CCC, I2C legacy, and hot join. Hot join must be initiated from an internal node. The list shows available internal nodes and their IDs. Use these IDs for hot join or IBI send. Node ID is also used in Python scripting. You can check it here or query it via the API. All commands use node ID. In the UI, this panel mainly serves as an ID reference. Now let's go through each node. First, address 8, the temperature sensor. It has 2 bytes of values. Let's perform a direct read. Check the report after sending. Set sub-address to 0. Send the sub-address, then perform a read to retrieve 2 bytes of temperature data. Now apply heat by covering the sensor. Hold briefly, then read again. The value increases due to heat. Remove the finger and read again. The value returns to ambient. Now let's perform read-write on an internal node. Target sub-address 0 on address A. Since nothing was written, the read returns 0. Now write a value. Send the write, then read back. The return data matches the written value. This confirms the write was successful. Now look at Broadcast and Direct CCC. Select a Broadcast CCC command from the drop-down list. HDR supports packet sending. Each packet includes an error injection panel. You can inject errors to test handling. Verify devices respond correctly to invalid frames. Switch to HDR mode and chain commands using restart. Each field shows bit level definitions. Now a direct CCC example. Set target count to define node count. Example, get PID for 8 and 9. Eight returns PID 023615. 9 returns its own PID. For get caps, results reflect capability bytes. That's all for quick send. Now, let's build custom packet sequences. Start with get PID. Set targets, for example, 3 nodes. The format is shown in the panel. Add a read from address 8, subaddress 0. Add a write to address A, subaddress 0. Then read it back, 4 bytes returned. Click OK to finalize. Back in the wizard, this is the sequence we just created: get PID to 3 addresses, followed by a read from the external temperature sensor, a write to the internal node, and a final read back from the internal node. Click Execute. Check the capture results. Get PID responses, the temperature read, the write to the internal node, and the final read back including the subaddress and 4 bytes of returned data. This is how you build the packet format for your test, and how you validate a complete test sequence with the PX2816B. Thank you for watching.